We're taking a look at section 3.5 using Newton's laws, and specifically homework question number 6 on page 147. If you look at the diagram provided, you see that there is a series of carts that are attached together, so there is tension in between each of the carts. Now, the carts are actually connected by force sensors. So between cart number 1 and cart number 2, there are force sensors 1 and 2. It is important to note that the tension in between these two carts will be equal. So whatever reading is on force sensor 1 will be equivalent to the reading on force sensor 2. So we're going to describe the force of tension in between force sensors 1 and 2 as the force of tension as read on sensors 1 and 2. Similarly, in between carts 2 and 3, we're going to represent the tension as the force of tension as read on sensors 3 and 4. And finally, in between force sensors 5 and 6, we're going to represent the force of tension as the force of tension as read on sensors 5 and 6. We established that the right direction is positive, and the question tells us that friction is negligible. So we can attempt to start our first question. And that question is, what is the acceleration of all of the carts? Now, we know that all of the carts will have the same acceleration because they are attached together. In order to examine this problem, what we're going to do is look at the last cart. And the reason we choose the last cart is because it has the fewest forces acting on it. So we'll be able to summarize its free body diagram much simpler than we could for the other carts. So I'm going to draw a picture of the last cart. And I know that the only force acting on this cart is the force of tension, and this is the force of tension as read by sensors 1 and 2. In order to proceed, we have to follow the same two steps we've been following for all of our Newton's second law problems, and that is list all of the forces acting on the object, being sure to indicate direction with plus or minus signs. So in this case, we have positive, the force as read on sensors 1 and 2. This is the only force acting on the last cart. The second step is to replace the expression F net with MA. So we have MA is equal to the force as read on sensors 1 and 2. Now we can sub and solve. We know that acceleration is equal to plus the force as read on sensors 1 and 2 divided by the mass. Including variables, the question tells us that the force that's read on sensor 2, which is equivalent to the force that's read on sensor 1, is 3.3 newtons. It's in the right direction, so it's positive. And from the diagram, we know that cart 1 has a mass of 2.2 kilograms. If we punch this into our calculator, we end up with positive 1.5 meters per second squared. So we can say the acceleration of all the carts is 1.5 meters per second squared forward, or right. Now I'm just going to highlight this because it's important to note that this is the acceleration of all of the carts. So if you find the acceleration of one cart, you know the acceleration of all the carts. In part B, the question asks us for what is the reading on each of the force sensors. So let's start with determining the force as read by sensors 3 and 4. We already know the force as read by sensors 1 and 2. That was given in the question, and it's 3.3 newtons. So let's determine the force as read by sensors 3 and 4, this force here. In order to do so, I'm going to look at cart number 2. So we draw a free body diagram of cart number 2. We know that cart number 2 is being pulled forward by the force as read on sensors 3 and 4, and is being pulled back by the force of tension as read by sensors 1 and 2. Follow the same two steps. The net force acting on cart number 2 is equal to plus the force as read on sensors 3 and 4 and minus the force as read on sensors 1 and 2. The second step is to replace the net force with the expression M2A and we can rearrange this for the force as read on sensors 3 and 4 is equal to M2A plus F1 and 2. Remembering that when we bring this term over the equal sign, its sign changes, and here we have it as positive. If we sub and solve, the force as read on sensors 3 and 4 is equal to 2.5 kilograms, which is given in the question, times 1.5 meters per second positive, second squared rather. We just calculated that acceleration in part A, plus the force as read on sensors 1 and 2, which was given in the question to be 3.3 newtons. If you punch this into your calculator, you end up with positive 7.1 newtons. So we can say the force as read on sensors 3 and 4 is equal to 7.1 newtons to the right. Next, we're going to look at the force as read on sensors 5 and 6. And in order to determine this force, we're going to look specifically at cart number 3. So we know cart number 3 is being pulled forward by the force of tension as read on sensors 5 and 6. It is also being pulled back by the force of tension as read on sensors 3 and 4. And we just calculated that one above. So to determine the force as read on sensors 5 and 6, we're going to list all of the forces acting on cart 3, using plus or minuses to indicate direction. So we get this expression. The net force is equal to plus the forces read on 5 and 6 minus the forces read on sensors 3 and 4. The second step is to replace F net with the expression MA. And using algebra to rearrange this, we get the forces read on sensors 5 and 6 is equal to M3A plus the force of sensors 3 and 4. Keeping in mind that since we brought this term over the equal sign, its sign changed to positive. So let's sub and solve. We have the forces read on sensors 5 and 6 is equal to 1.8 kilograms from the question, positive 1.5 meters per second squared from part A, plus the forces read on sensors 3 and 4, which is 7.1 newtons, which we calculated up above. Punch this into your calculator, and you end up with positive 9.8 newtons. So we can say that the forces read on sensors 5 and 6 is equal to 9.8 newtons to the right.